Thanks everybody for being here today. Let's go ahead and get started with Bryce's defense. So I'll just give a little introduction. So to give you some background on Bryce, he graduated with his bachelor's degree from mechanical engineering from the New Jersey Institute of Technology, and then went on to get a master's degree working with Klaus Lackner. Some of you might know. He years ago was here at Stanford, actually worked at SLAC, and he's a physicist. Bryce did his master's degree at Columbia University with Klaus, looking at CO2 capture, and then came here to Stanford in the Energy Resources Engineering Department. Has been working with me on this very interesting topic. Before I talk a little bit about that, I'll just give you a little bit of background on Bryce from a personal perspective. One thing I can say about Bryce is that he's probably, sorry for those of you that are current students in my group now, but I think you'd all agree he's probably the nicest person you'll come across. And in the department, it's like if anybody needs a hand with anything, he's always there to help. And I would say, too, his skill set is extremely unique. His background is in mechanical engineering, but his dad and his brother are both mechanics, and so he grew up, being very hands-on. So anything that needs to get done in the lab from a mechanical perspective, Bryce is on it. No matter, I even have this old table from Target that we used to keep our computer on, and I actually had it in my house back in Massachusetts before I came here. And Bryce took it all apart and rebuilt it for a setup for one of our packed bed reactors. And it's like a $40 table from Target. And it's like anything he can rebuild and start over. And he doesn't just ask folks in the machine shop to do it for him, because he knows how to use the lathe and all of the different components in the machine shop he's actually familiar with. So you can really do the work and the machining and everything from start to finish. So now talking a little bit about his project, not straightforward at all. I think a lot of you know just your background of being in this department or at least affiliated. One of the big issues with CO2 emissions is dealing with the transportation sector. And one especially difficult sector within transportation is long-haul trucks. And the question is, what do we do in terms of CO2 emissions associated with those, which represent 25% of transportation emissions? And so one of the things that we were thinking about is, can we capture CO2 on board the vehicle? Can we think of a strategy where we can potentially use hydrogen to fuel the vehicle, but rather than worrying about the storage of hydrogen, make hydrogen in real time on the vehicle, such that you're feeding it into a fuel cell or a hydrogen internal combustion engine. And so that's the project that Bryce has tackled. And there's a lot of different components to it, because there's catalysis involved, but then there's also metallic membrane separation for the hydrogen, because you need to produce hydrogen at very high purity if you want to feed it into a fuel cell. And so this project is really tricky because it ranges from catalysis and catalyst design all the way to membrane separation. And Bryce doesn't just do experiments in the lab, but he also has actually fabricated the membranes themselves. So in his PhD, he's visited Worcester Polytechnic Institute, which is where I was at before Stanford, and actually worked in the lab there for a few weeks to actually make the membranes that he's tested, that he'll show you the results on today. From Massachusetts, he flew to Italy and worked at another lab in southern Italy for another extended period of time to test similar membranes in the configuration that they have in Italy, because you can kind of count on one hand the number of groups in the world that do this kind of research, and that just happens to be one of them. And WPI happens to be a second one, and we happen to be a third one here. So there's just a very small number of groups that are doing this kind of work. And oftentimes, the groups, like for instance at WPI in Worcester, they do one component, a small component, where they make these metallic membranes and they measure fluxes. And in Italy, they might test them such that you have the catalyst and the flux in one, that you'll see Bryce has done today. But the unique thing that Bryce has done is he's actually taken this from fabrication to testing and then application to a specific problem for transportation. And none of these groups are really tackling it the way he has. And also, just as a complete confession, this is not even he's the first person in my group to actually do these kinds of experiments. And so he's really tackled something very challenging. And I think you'll see today from the broad range of results that he'll show you from his work, and also this child that he's created here at the end of his time kind of is a testament to his efforts and his motivation for this work.
All right. Thank you, Jen, for that wonderful introduction. Thank you, everyone, for coming today. It's an honor to talk to you today. So let's get into it. So the topic here is onboard hydrogen production from natural gas via palladium-based membrane reactors. So as you can see here, the objective of this entire PhD dissertation was to produce pure hydrogen. And how I did that was I used, as we alluded to, the membrane reactor as a tool in order to achieve this pure hydrogen. In order to do this, I took natural gas and natural gas steam reforming within the membrane reactor to produce that pure hydrogen. Now, the idea is to take that pure hydrogen and feed it into a PEM fuel cell. This PEM fuel cell can then be used for the transportation sector. The reason I picked a PEM fuel cell is that it has a low operating temperature, as well as the emissions is only water. Furthermore, as a co-benefit of this membrane reactor is a high concentration of CO2, in which there's potential to capture that CO2, thus mitigating emissions from the transportation sector. A little bit of an overview of some of the results I'm going to show. I'm going to talk about the fabrication of these hydrogen selective membranes. Then I'm going to get into the performance of a membrane reactor, that is MR here, using a pure palladium porous stainless steel supported membrane. Again, by using the steam methane reforming reaction. By two different feeds here, you'll notice here CO2. This is a common component within natural gas. Again, the idea here is to use natural gas in the end. And these conditions I'll get into a little bit later. The next membrane reactor I'm going to talk about is pure palladium on a ceramic supported membrane. Similarly, steam methane reforming. You can see here there's two different kinds of feeds. Here you can see nitrogen as well as CO2. Again, both of these are common impurities within natural gas. Some of the conditions here. And the final membrane reactor I'm going to talk about is an alloy that has a palladium gold supported on porous stainless steel. And with this I'm going to use natural gas specifically, and that is the mixture of hydrocarbons as well as CO2 within the mixture. So bring it up a notch. And here's the conditions here. And then briefly at the end, I'll talk about the feasibility of this for onboard application. So a little bit of an overview of the talk. I'm going to talk about the motivation for this work, introduction, that is for the commercial hydrogen production currently in the world, and then hydrogen production via the membrane reactor. Furthermore, I'm going to talk about the fabrication of the palladium-based membranes, some experimental results, both using steam methane reforming and natural gas reforming. And I'll give a real-world example at the end. All right, let's get into it. So the motivation here, as we all know within this department, we can see historically that world energy consumption has been on the rise and is projected to be on the rise within the future. Specifically, if we see here, fossil fuels make up about 80% of this increase. And if we look even more specifically at natural gas, this is the fastest growing fossil fuel at about 2% per year. What does all this fossil fuels translate into? CO2 emissions. We can see here from the developed countries, we're already at an elevated level. If we look at the developing countries, there's a significant increase in CO2 emissions. All these CO2 emissions have been directly correlated with global temperature rise, which of course we would like to mitigate. So let's look at the US specifically here. If we see from this chart here, this is the greenhouse gas emissions for the US specifically. And if we see here for transportation is 26% of those emissions, so a significant portion. If we look at the broader scale that is global, we can see vehicle ownership. So currently there's about 1 billion vehicles on the planet, and it's projected to increase to 2 billion between 2030 and 2050. All these vehicles translates into more CO2 emissions into the atmosphere. But if we could potentially use hydrogen, maybe we can offset those CO2 emissions. So you can ask yourself, where does hydrogen come from? Well, globally, there's about 4 different sources of how hydrogen is produced. We look specifically here at natural gas steam reforming. It makes up almost half of that hydrogen production currently. So let me talk briefly about how this process works. So it's a multi-step process. Let me start on the left here. You can see this methane and steam enter the reformer. This reformer here is at between 800 and 1,000 degrees Celsius, so quite a high temperature. Governed by these reactions here, you can see some of the products of the reaction here. These products enter into the 2 more reactors for removal of CO, shown here. Furthermore, the products here, governed by this reaction, enter into the hydrogen purification. This is where the pure hydrogen comes out. As, of course, a byproduct of this, there's a significant amount of CO2 that's mostly vented to the atmosphere. So you may ask yourself, well, this process seems pretty large. There's multiple steps. Is there a solution that we have where we can do all of these in one? There is. That is the membrane reactor. We can take this reforming process as well as the two reactors plus the purification and separation of hydrogen in one unit. All these steps into one. Powerful. So let me talk a little bit of how the membrane reactor works. So here's a cutaway of the membrane reactor. We can see here hydrocarbons, so natural gas, and steam enter into the reactor. They convert into hydrogen here across the catalyst. The palladium-based membrane allows for it's only selective towards hydrogen. That is, only hydrogen can permeate through the membrane, shown here. We can enhance this permeation of hydrogen through the membrane by applying a sweep gas through the permeate side of the membrane, as shown here. And the pure hydrogen comes out on this end here. On the back end, we have the admissions here, and this is known as the retentate side. This is the outlet of the reactor. So now, I showed you the membrane reactor technology. So how does it fit here within the US? Well, I believe it fits very well, and that is we can utilize the built infrastructure of the natural gas pipelines. We can see on this map here that natural gas pipelines, they're quite significant throughout the United States. Furthermore, there's about 1,700 compressed natural gas stations already within the United States, shown here. You can see there's multiple here within the Midwest as well as the East Coast. Furthermore, this membrane reactor for onboard application can be a possible solution for distributed emissions, which there currently is no feasible technology for that. And the reason I propose that is because on the retentate side here, it's a CO2-rich stream that comes out. And there's possible that this can be a bridge for sustainable technology to come in the future. So let me talk about why I chose the palladium-based membranes. So we see here there's a good amount of membranes for hydrogen separation. That is metallic, polymeric, carbon, as well as two different ceramic type membranes. Let's look specifically here for the metallic at the hydrogen selectivity. We can see here that it's greater than 1,000. And if we compare that to these other ones, it's significantly greater. Of course, the idea here is to produce pure hydrogen. So that's a winner there. Furthermore, if we look at the material used within this metallic membranes, it's typically pure palladium as well as palladium alloy. Palladium alloys are used to overcome some of the negative implications of using pure hydrogen. That is hydrogen embrittlement that happens with pure palladium, as well as being poisoned by sulfur. And specifically, sulfur is H2S. That's hydrogen sulfide, which is also a common impurity found within natural gas. So again, we can overcome these limitations of using pure palladium by alloying that with another metal. And I'll get into those details a little bit later. So metallic here is the clear winner. So let me go into a little bit of how the fabrication of these hydrogen selective membranes were fabricated. So I was personally able to fabricate 6 of these membranes, as Jen mentioned, at Worcester Polytech Institute in Worcester, Massachusetts. And specifically, I used 2 different supporting materials of several that can be chosen. So here, ceramic and porous stainless steel. So let me briefly talk about ceramic. So the reason I use ceramic is that the supporting material is characterized by small pore sizes, that is on the nanometer scale. Furthermore, ceramic is typically cheaper than some of these other supporting materials. If we look here at the porous stainless steel is good from a mechanical standpoint. That is, its stability is very well after the deposition of the layer on top. Furthermore, the thermal coefficient of expansion is very similar to that of palladium, or the palladium alloy that will be deposited on it. But unfortunately, for the porous stainless steel supports, they have pretty high pore sizes. That is on the micron scale. So a little bit of details here. For ceramic, I made 2 pure palladium membranes. And for the porous stainless steel, I made a pure palladium, as well as a gold palladium gold, palladium gold palladium, and palladium gold. I tried to get all the combinations there. So specifically today, I'm going to talk about 3 different membranes, these 3 highlighted here. But before I talk about those membranes, let me briefly introduce how these membranes are actually made. So this is a multi-step process via two different plating techniques. That is, it's electroless plating for palladium, and it's electroplating for gold. So we started, for this specific example I'm going to show here, I started with the porous stainless steel support. You might notice here this color. This is actually a zirconia layer on the porous stainless steel support. These porous stainless steel supports are obtained commercially. So what I had to do to prep this area is I had to actually sand that down a little bit, because it's potentially that the zirconia layer is a little bit too smooth for the deposited layer to come. So after the sanding, there's an intermediate layer. This intermediate layer mitigates the intermetallic diffusion between the palladium layer that's about to come and the porous stainless steel support below. So after this intermediate layer, first palladium plating, second, followed by a second, and then again, in this specific case, there was gold on top of that palladium, and then this was followed by a final palladium plating layer. That final palladium layer is to enhance the hydrogen flux initially when the membrane is brought up to temperature. So the whole point of this process here, shown in the schematic, this is the undesirable case. That is, if I put this metallic layer and it doesn't bridge the supporting material below, it'll allow the permeation of all gases to flow through the support. Of course, the idea here is to be completely selective towards hydrogen to get that pure hydrogen that I would like. So we can see in the desirable case, the metallic layer bridges the support below and it's only selective towards hydrogen. So now let me talk a little bit of how actually hydrogen permeates through the metallic layer. So shown here, this is the high pressure side, that is the feed side of the reactor. Hydrogen, H2, adsorbs to the surface, shown here, then dissociates into atomic hydrogen, H and H, diffuses through the metallic bulk here, recombines on the low pressure side into H2, and then desorbs. Again, the low pressure side is typically referred to the permeate side. This whole process is governed by an equation, as shown here. This is the hydrogen permeating flux equals the permeance of the membrane times the partial pressure of hydrogen in the retentate side, that is the high pressure side, to the power of n, minus the partial pressure of hydrogen in the permeate side, that is the low pressure side, to the power of n. And the power of n is typically between 0.5 and 1. And I'll get into, in just a few slides, some more details about the n value. Furthermore, another equation, this is the permeance, this is this p-value here, is equal to the pre-exponential factor times the exponential times the negative activation energy divided by the universal gas constant times temperature. The important thing to know from this equation here is that if we increase temperature, we increase permeance, thus increasing the hydrogen flux through the membrane. And just one more equation, not too many. It was ideal selectivity. That is the permeance of hydrogen over the permeance of another gas, typically an inert gas. For here, I'm going to concentrate on using argon as well as helium. Now, for this ideal selectivity, this is an important parameter. That is, I want this to be infinite. That is, I only want it to be selective towards hydrogen. So let's get into some of the results here. This first set of experiments is with the membrane reactor using pure palladium on porous stainless steel. So shown in this picture is my second home here at Stanford, sometimes my first home, of course. Let me walk you through what this is here. So we have the feed as well as the water, and essentially I want that into steam. That enters in this preheating zone. Again, this preheating zone brings the feed and the water up to temperature, so that when it enters into the reaction zone, it's up to temperature already. All these experiments were characterized via a mass spec, and this mass spec can go down to, it can detect parts per billion, so very accurate. If we look a little bit here at the reaction zone, we can see this is the membrane reactor, as showed earlier. In this membrane reactor, I had 3 grams of a nickel-based catalyst, obtained from Johnson Matthey specifically. And the membrane here used was a pure palladium porous stainless steel supported. A little bit of the details here. The palladium layer was 13 microns thick. The active length of the membrane was 14 centimeters, and the outer diameter was 1 centimeter. Before we get into the reaction testing, we need to characterize the membrane. That is, first we provide the reactor with pure hydrogen to obtain that n value that I'm just about to talk about. You can see from this graph here, I take the hydrogen flux at various pressure conditions. That is the differential and partial pressure of hydrogen in the high pressure side minus the low pressure side. And I fit these flux values to various n values. That is the power of n in this equation between 0.5 and 1. And I know from literature as well as it's been shown that the n value is between 0.5 and 1. And for an n value of 0.5, if I found an n value for 0.5, that means the membrane should only be selective towards hydrogen. But shown here, you can see a slight deviation from 0.5. That is 0.6. This indicates that the membrane will not be fully selective towards hydrogen. So then you ask yourself, well, how selective will it be? Well, we further characterize that with the ideal selectivity, as shown earlier. And we can see here at the two lowest pressures, the ideal selectivity was infinite. But when we increase the pressure, that ideal selectivity decreases. Now, to put these numbers into context, there's a DOE target of the ideal selectivity of hydrogen to nitrogen of about 10,000. So you can see that these values here are in agreement, and the hydrogen-argon values specifically are greater than that target. So that indicates that the membrane should perform well. So now we can get into the reaction testing. For this set of results I'm going to show, I varied the reaction pressure as well as the argon sweep rate, again using the steam methane reforming reaction. The conditions, the reaction temperature was 400 degrees Celsius. Again, if we think back to that commercial application I showed earlier, the temperature is 800 to 1,000 degrees Celsius. We can see we're half of that. Furthermore, the gas hourly space velocity, this is defined by the volumetric ratio of the feed divided by the catalyst volume. And here specifically it was 2,600. Furthermore, shown here is the steam to methane ratio. That is, here I use 3.5 to 1. We see here theoretically is 2 to 1. That is, for every 2 moles, there should for every 1 mole of methane, there should be 2 moles of water. But the reason I use an excess of steam is twofold. One, if I have an excess of steam, I can promote this reaction towards its products, thus making more hydrogen. And secondly, I use an excess of steam to mitigate the coke formation within the reactor. So let's show some results here. As you can see here, I have the methane conversion plotted against the reaction pressure. Let's take, for example, the 100 milliliters per minute line here as a sweep rate. As we increase that pressure, we can see that the conversion increases. But from a thermodynamic point of view, if we look at this reaction here, it increases with a mole number. So by increasing the pressure, that should negatively affect the conversion. But we see an opposite trend. And this is owing to the flux equation here. If we look, what we're doing is we're increasing the high pressure side of the reactor, thus providing a higher flux of hydrogen. Again, what we're doing here is we're pulling the hydrogen out via the palladium membrane. What this does is it shifts the reaction towards its products. This is known as the shift effect. I'll refer to that quite often. Furthermore, if we look at the various sweep rates here, that is, if we pick one of these pressures, say 200, and we look at 0 and then increase that to 100, what we can see effectively is there's an increase in the methane conversion. The reason this takes place is that we're decreasing the partial pressure of hydrogen in the permeate side. Again, increasing the hydrogen flux, thus shifting the reaction. As we see here, I was able to obtain a methane conversion of 84% at the two highest conditions here. Furthermore, you may be asking yourself, what's the star here? This is for the fixed bed reactor testing that I did that I don't have time to talk about today, but I have in my dissertation. These set of experiments, there was no membrane. That is, it was at the same pressure and temperature, but there was no membrane involved. And we can see here that the conversion obtained was just 32% at 275. But if we see, by using the membrane reactor, that is without any sweep gas, we are able to overcome this conversion limitation. So if we look here specifically at the hydrogen recovery is defined by the pure hydrogen in the permeate side divided by the total hydrogen produced. So if we look here, we see a similar trend as we did for the conversion. If we look at 0 here, as we increase the pressure, we increase that hydrogen conversion, again, owing to the higher flux of hydrogen through the membrane. Furthermore, as we increase the sweep rate, we can see a higher hydrogen recovery. And for this specific set of experiments, I was able to obtain 82% hydrogen recovery. That is, I was able to obtain 76 milliliters per minute of pure hydrogen from this process. Furthermore, I'd like to point out that the hydrogen permeate purity here was 100%. That is, only hydrogen was detected via the mass spec. no other species. Another set of experiments I tried was adding carbon dioxide to the steam methane reforming reaction. This was twofold. One is that it's commonly found within natural gas, as mentioned earlier, at about 3 volume%. Furthermore, it's a product of the steam methane reforming reaction. That is, if we add a product of the reaction, it should negatively affect the conversion of methane. So let's see what some of those results look like. For this set of experiments here, I use 6 volume%. That is, I use double what is commonly found within natural gas. We can see here by using just a 25 milliliter per minute sweep, we can see that negative effect I talked about. That is pure methane relative to methane with CO2. We see a decreasing in methane conversion. But I have a solution to overcome that, or potentially mitigate that. That is, you can increase the sweep rate within the reactor. As shown here, you can see we can mitigate those negative effects of adding CO2 to the feed. Furthermore, we see a similar trend here for hydrogen recovery. That is, at the lower sweep, we see a larger delta than we do at the higher sweep rate. Again, this is owing to the membrane's ability to permeate hydrogen. And specifically here, for using CO2 with the steam methane reforming reaction, I obtained 38 milliliters per minute of pure hydrogen production. So now you may think, well, Bryce, this is cool here, but you're using argon as a sweep gas, and you told me the hydrogen is pure, but now we have argon as well as hydrogen, which is a separation issue. So if we think of the onboard application, what can we do for that? Well, we can provide steam in the permeate side, which is easily condensable, thus can be used for onboard application. So let's look at what those results look like. So here I have compared argon in the green to steam in the blue. You can see that the results are similar. That is, for using argon as well as steam, I get similar results. And furthermore, you can see here for the hydrogen recovery, also similar results. This is important because, as mentioned, that the steam can be used for the onboard application purposes. Furthermore, in the experimental testing, it's actually easier to use argon as a permeate. It's just one less complexity to the testing. So now, after these reaction testings shown, as well as others that I'm not mentioning here today in the interest of time, we can analyze the life of the membrane. That is, we can see from this plot here the ideal selectivity of hydrogen to argon. We can see initially it was infinite, that is, only selected towards hydrogen, but decreases over the experimental time. The total life here was 750 thermal hours, that it was up to temperature for that long. And of those 750 hours, 500 of those, it was under reaction testing. If we look specifically here, if we compare the first test with the membrane reactor as well as the last test, we can see that the ideal selectivity decreased from infinite to just 30. If we look, as we look down this chart here, we can see that all the parameters decrease. We can see specifically here, I would like to point out that the hydrogen permeate purity, instead of being 100% as it was initially, decreased to 90%. But importantly, I would like to point out that there was no CO detected in the permeate side. This is important if we would like to feed this to a PEM fuel cell, because only a few ppm of CO can actually poison the platinum catalyst within the PEM fuel cell. So I wanted to investigate why this, or potentially why this ideal selectivity was so low. So here's the membrane. On the top here, this is a fresh membrane, and below this is the membrane I just showed after the reaction testing. With the naked eye, there's no visual difference. Of course, you may be seeing this black line here. This is just from extracting the membrane from the membrane reactor. This did not take place during the reaction. So I wanted to zoom in a little bit further and look at that surface. So I took some SEM images of the palladium surface. As we can see here, highlighted in these red circles, there's actually holes within the palladium layer. If you look specifically here, it's very clear that there's a hole within that palladium layer. Again, allowing the permeation of all gases through the membrane. Thus, we had this low ideal selectivity. So the conclusion of these results here, by operating at these low temperature of 400 and a low pressure of 300 kilopascals, I was able to achieve a methane conversion of 84%. Furthermore, hydrogen recovery of 82%. That is, I was able to obtain 76 milliliters per minute of pure hydrogen. As shown, the membrane reactor allows for the shift effect. That is, as the hydrogen permeating flux increases, so does the conversion of methane. Furthermore, I showed that the membrane reactor mitigates the negative effects of adding CO2 to the feed. That is just a 3% difference for the conversion, just a 2% difference for the hydrogen recovery. Furthermore, I showed that the pure hydrogen can be obtained by using steam as a sweep. Again, this is important for the onboard application purposes. Towards the end of the membrane's long life, unfortunately, it was not fully selective towards hydrogen. But as a potentially benefit, there was no permeation of CO within the permeate side. So I thought, well, given the membrane degraded over time, is there a way to maybe overcome that limitation of the membrane degrading? So I tried the palladium membrane supported on the ceramic support. For this experimental testing, took place at the Institute of Membrane Technology. As Jen mentioned earlier, I was able to go there in Calabria, Italy, the southern part of Italy, for 1 month and perform some reaction testing. And here's the membrane. That is the palladium with the ceramic supported membrane. Specifically, the palladium layer, 11 microns here, the active length, 7.4 centimeters, outer diameter of 1 centimeter. And before reaction testing can start, I did the hydrogen permeation test to find the N value of 0.6 at 400 degrees Celsius. Again, most likely the membrane will not be fully selective towards hydrogen. So let's look at that module that I used. Here we have the feed that enters the reactor. This is the retentate side on this side. And then you can see here, this is the sweep gas that comes through the core of the membrane and provides that pure hydrogen on this side, the permeate side. More specifically, this membrane was held within here via 2 graphite gaskets. That is, those graphite gaskets hold the membrane in place to minimize the leakage between the retentate and the permeate side. That is, when we analyze the permeate side, we know that any gases that are there permeated through the membrane. And specifically here, I used just a ½ gram of nickel-based catalyst. The operating conditions here are similar to those of the previous experiment. I'd like to note here, instead of using argon, I used nitrogen sweep. Let's look at the results. Here I have 2 different mixtures. The first mixture is the steam methane reforming reaction. That is methane plus steam plus 3% nitrogen. And the second mix is the same steam methane reforming plus nitrogen as well as CO2. The reason I use CO2 and nitrogen is because these are common impurities found within natural gas. Again, the end result here is to use natural gas. We can see with these 2 different mixtures that there's a minimal difference between methane conversion and hydrogen recovery. Again, this is owing to the membrane's ability to selectively permeate hydrogen, thus shifting the reaction. Furthermore, I looked at the influence of the space velocity. That is, as I varied the space velocity, we can see a decrease in the methane conversion. This is due to an increase in the space velocity is less residence time within the reactor. That means that the reactants have less contact time with the catalyst. If we look here as a benefit of this reactor, the hydrogen recovery was high. That is 92% for the lowest space velocity. But unfortunately, if we look at the hydrogen permeate purity here, just 72% was obtained at the lowest space velocity, so not pure hydrogen. So I took the membrane out. I wanted to analyze what went on here with the membrane, because clearly something was wrong. So again, some SEM images. Here is the cross-sectional analysis of the membrane. That is, we can see the palladium layer here on top of the ceramic support. If you look here, you can see that it appears as though the adhesion of the palladium layer is not very good with the ceramic below. This further drives home that point. As you can see, the palladium layer here appears to be peeling off the support below, and also shown here. So unfortunately, this membrane didn't perform very well. That is, the support below maybe was too smooth, and/or there was an error in the fabrication process. So the conclusions from this experiments here, there was similar performance for using both steam methane reforming and nitrogen, as well as nitrogen and CO2. At the lowest space velocity, hydrogen recovery was 92%, quite high, but unfortunately, the permeate purity was 72%. That is that the membrane degradation led to this poor performance. So I just showed 2 pure palladium membranes on 2 different supports. Now I'm going to show an alloying, that is palladium gold, on porous stainless steel with this natural gas steam reforming reaction. This is the exciting stuff. So this membrane here was the deposition of 2 different metals, that is palladium and gold. And the reason I chose gold here is twofold. That is, the hydrogen permeability will actually be higher for this alloy at 5 weight % of gold, as well as it's resistant to sulfur. That is, it potentially resistant to H2S that's, again, commonly found within natural gas. I won't talk too much today about H2S, but I do in my dissertation on some other experiments that I won't go over today. Let's look at the membrane. You can see here, here's the permeable area. You can see that gold layer below. Again, on top of this layer is the palladium, which I'll show in just a minute. We see the total layer here is about 14 microns. The gold percent is 5 weight percent. That is, this is known to be a higher permeability, which is why 5 weight percent was chosen. Active length of 3.6 centimeters, outer diameter of 1 centimeter. So I'll show you a schematic. Again, I started with that porous stainless steel support with the zirconia layer that was commercially obtained. 2 layers of palladium deposited, followed by gold as well as the palladium on top. As mentioned, the palladium on top allows for an enhanced hydrogen flux initially when the membrane is brought up to temperature. Furthermore, as the membrane becomes an alloy, that is, there's an induction period needed to actually interdiffuse these 2 metals together. So this can also help with that, having this sort of sandwich of the metals. So this induction period, let me talk about that. So here from this plot, you can see the hydrogen permeate flow rate versus the experimental time. Initially here is where this annealing process takes place. That is, pure hydrogen was fed to the reactor, and the temperature was increased. So the membrane is brought up to temperature to 350 degrees under an inert gas. At 350 degrees, I feed pure hydrogen to the membrane reactor. When the permeating flow rate is constant, I increase that temperature. And I stepped it up to the operational temperature of 450 degrees Celsius, which is the recommended operating temperature for this membrane. When the flux was constant, I'm able to perform the reaction testing. But during this annealing process, I was able to characterize the membrane. That is, if we look at these 2 lower temperatures, an N value of 0.5 was obtained. That is, the membrane should be completely selective towards hydrogen. Again, further characterizing the membrane, we can see that the ideal selectivities here show infinite. That is, it's only selective towards hydrogen. No other gases permeate through the membrane. Unfortunately, though, when I increase that temperature to 450, I can see a slight deviation from 0.5. That is 0.53, which indicates that the membrane will not be fully selective towards hydrogen. But we can see here at the lower pressure, the ideal selectivity was infinite. But as we increase the pressure, the ideal selectivity decreased. Again, if we remember that DOE target is 10,000 for hydrogen to nitrogen. You can see that here for the argon results, they exceed that value. And after, I'm going to talk about the reaction testing here, which was in this time frame. So some of the reaction details. Again, here I use natural gas steam reforming, and I'll compare that to pure methane steam reforming. The conditions are similar to those in the previous, but here I use the reaction temperature of 450 degrees. Again, this is related to the membrane's operational temperature. Furthermore, composition of natural gas similar to pipeline quality. So I obtained data from PG&E from the Bay Area, shown here, of the various hydrocarbons as well as the impurities of nitrogen and CO2. And this is the experimental gases that I used. As you can see here, they're in good agreement with the pipeline quality. So some of the reactions that take place, you can see here there's a significant amount of reactions that can take place within the reactor. That is owing to each one of the hydrocarbons respectively for their steam reforming. Shown here are just some of the dominant pathways of these reactions. Specifically, I would like to point out that some of these, ethane and butane, can actually produce methane within the reactor. For hydrocarbon conversion, I'll talk about, that's the flow rate of the respective hydrocarbon in minus the flow rate of the respective hydrocarbon out, divided by the flow rate in. All right, let's get into the results. So here I show pure methane. Again, this is with the same reactor. A pure methane feed here and natural gas feed. You can see for natural gas that the methane conversion was lower. There's potential here that the formation of methane actually is part of this gap. That is, within the membrane reactor itself, the conversion of methane may have been similar to that of pure methane. But owing to the formation of methane, we see here a decreasing conversion. Let's look at the hydrocarbons. So we have here butane, propane, and ethane. As we see here, as we increase the pressure, we see an increase in conversion. Again, if we look at these reforming reactions, they proceed with an increasing mole number. That is, from a thermodynamic standpoint, as you increase the pressure, these conversions should decrease. But owing to the membrane's ability to shift these reactions towards their products, we can see an increasing conversion as we increase the pressure. So specifically here, let's look at some of the hydrogen recovery. We can see here for natural gas that the hydrogen recovery is higher when compared to methane. This, if you look at these steam reforming reactions here, we can see that each one of their respective hydrocarbons produce more hydrogen per reaction. So I would expect there to be more more hydrogen for the natural gas. Specifically here, at the highest pressure, I was able to obtain 51 milliliters per minute of pure hydrogen. That is natural gas into the reactor, pure hydrogen out. If we look here at the CO selectivity, defined by the equation here, but the CO selectivity is just a fancy word for the composition, that is the CO composition, within the retentate side of the reactor. We can see here as we increase the pressure, the CO selectivity decreases. This is owing to the water-gas shift reaction. That is, as the membrane is allowed to selectively permeate hydrogen, we can shift this water-gas shift reaction towards its products. And here at the highest pressure, CO selectivity of 0.62% was obtained. And now, if we look at the CO2 selectivity here, we see similar to that of hydrogen, that is increasing. Again, this is owing to the shift effect. Specifically here at the highest pressure, we can see that the composition of CO2 in the retentate side was 27%. So I want to look at the temperature effect on the membrane reactor. That is, that varied the temperature between 350 and 450 degrees Celsius. As shown here, as I increase the pressure, we can see an increasing in conversion. The reason for this is twofold. That is, from a thermodynamic standpoint, these are endothermic reactions. That is, as we increase the temperature, the conversion should increase. Furthermore, as I showed earlier, when we increase the temperature of the membrane, we can increase the hydrogen flux, thus further promoting these reactions towards its products. So again, we can see here an increasing in conversion. Let's look at the hydrogen. We can see here for the hydrogen permeate in this line, this blue line here, at just 350 degrees Celsius, I was able to obtain about 20 milliliters per minute of pure hydrogen production. If we increase that to 450, you can see that the flow rate of pure hydrogen was 60 milliliters per minute. Again, this hydrogen here was pure. That is 100% pure hydrogen. Another important test to be done if this was going to be used for onboard application is the longevity of these reactions. That is, the membrane's ability to produce hydrogen in a long term. So here I did natural gas steam reforming for 240 continuous hours. That is, I started these reaction testing after other experiments were done. That is, the membrane reactor was not fresh. You can see here I started at 250 reaction hours. You can see across all 240 hours, the conversions are all constant. That is, no deviation in performance of the membrane reactor. Furthermore, if we look at hydrogen permeate purity, that was 100%. That is, only hydrogen was detected in the permeate side. If we look at the hydrogen recovery here, it was constant about 55%. That is, we were able to gather about 55% of the produced hydrogen. And specifically here, over this 240 hours, I was able to obtain 700 liters of pure hydrogen. Let's look at the total hydrogen. If we see here, these are the products of the reaction. The total hydrogen produced was 1,100 liters. To note here, the CO production was very low, which is good. That is, if there's a minimal partial pressure of CO, that will mitigate the potential permeation of CO into the permeate side. Again, we don't want to poison the palladium. We don't want to poison the PEM fuel cell. If we look specifically here at the CO2, that is, the composition of CO2 is 22% in the retentate side. So I thought to myself, am I able to capture the CO2 potentially, or separate that out from the reaction? So shown in this box here is where I actually tried to separate some of the CO2. So let's look at that. You can see here that the flow rate of CO2 was constant, and then I brought on that CO2 separation unit. You can see the flow rate decreases to 0. I took it off the separation unit and increased back to its original flow rate. Again, over here I put the separation unit back on. And here's a picture of that CO2 solid form. So after 1,000 hours of reaction testing, I wanted to analyze the membrane further. So again, I was able to find the ideal selectivity. So there was just a slight decrease from the data shown earlier here at 450. But you can see we're still above that DOE target of 10,000. Furthermore, at these lower temperatures, we're still completely selective towards hydrogen. That is, only hydrogen can permeate through the membrane. This is after 1,000 hours of reaction testing. So the membrane still showed good performance. So I looked specifically further at the palladium surface. That is, you can see these modules here. This is characteristic of a palladium surface. These are kind of known as the cauliflower shape. You can see here that there's no visual holes within the palladium surface. Furthermore, if I analyze the membrane, if I took it out, you can see the gold initially of the membrane, but there's no gold anymore. So I wanted to analyze how did that composition turn out. That is, how did that alloy turn out? So here's a cross-sectional analysis using EDS. You can see this is the supporting material below, and this is that palladium gold layer here. So here, shown in red, is iron, characteristic of steel. Again, that's the supporting material below. Then you can see the yellow here is the zirconia layer. That is, this was commercially obtained with porous stainless steel with the zirconia on top. Now let's look specifically at that metallic layer. You can see here in the blue, again, this blue color here is owing to the fact that the EDS, the signals of gold and zirconia overlap. So just ignore this blue here. But you can see the gold, there's a nice gold-rich layer on that top of the membrane. Again, this membrane was palladium gold palladium layer. And you can see that the blue here is within the palladium bulk. That is, if you see here with the palladium, there's a nice overlap, again with that gold-rich layer on the top. So the conclusion of this portion here is that at these low operating conditions, again, if we think about the commercial aspect, that is, the temperature is between 800 and 1,000, we're still less than half of that. Furthermore, the conversion for the ethane, propane, and butane were greater than 75%. And the hydrogen recovery here was 69%. That is, I was able to obtain 60 milliliters per minute of pure hydrogen production. Long-term reaction testing for 240 hours showed no decrease in performance. And I was able to obtain about 700 liters of pure hydrogen. The membrane performance was stable for 1,000 hours, and as I showed, that the alloying was good between the palladium and the gold, with that gold-rich layer on the top. So these experiments concluded that the membrane reactor can produce pure hydrogen by feeding natural gas. I'm going to talk here briefly about the feasibility of this for the onboard application. That is, if we look at the current fuel cell vehicles on the market, in order to achieve that 300-mile mark with every fill-up, you need about 5 kilograms total of hydrogen. Or at highway speeds, you need a flow rate of about 1 kilogram per hour. So how many of these membranes, that is about this size here, how many of these are needed in order to produce this flow rate of hydrogen? So we can see here at the low delta P of 200 kilopascals, we need about 190 of these membranes. But if we increase that pressure, we only need about 40 of these. Now, I'd like to point out, you may be thinking, well, you increase the pressure, and there's an energy penalty associated with that increase in pressure. But the idea here is to potentially use compressed natural gas on board. And compressed natural gas is at about 25,000 kilopascals. We can see an order of magnitude difference in that pressure. So how much volume will this take up? That is, how much space on board a vehicle will the membrane reactor plus the natural gas and water needed for the reaction to produce that pure hydrogen? How much room will that take? Well, that's about 120 liters on board the vehicle, which is roughly the hydrogen storage for some fuel cell vehicles currently on the market. Or, to put that in context, is about double the average gasoline fuel tank. So this will take up about 30 gallons of space, if that helps. So the final conclusions here of this study was that the membrane reactor performs better than the traditional reactor. This membrane technology allows for pipeline quality natural gas feed to produce pure hydrogen. Long-term testing showed that the stability of the membrane, there was no decrease in performance for 240 hours. The palladium gold membrane operated for greater than 1,000 hours, again, without a decrease in performance. This membrane technology can be an effective tool to mitigate the CO2 emissions from the transportation sector. That currently is no viable solution. And as I showed, we can use the natural gas pipelines throughout the US. The hydrogen produced is fuel cell ready. And furthermore, the byproduct is a high concentration of CO2. Now you may be thinking to yourself, Bryce, that's cool, you showed me some of these results, but I would like to actually see this hydrogen fed into a fuel cell vehicle. I got a solution for you. We see here from the video, this is the membrane reactor in the back here. This yellow tube is providing pure hydrogen to this little fuel cell vehicle. And this is at 350 degrees Celsius.
Who's the driver?
It's the self-driving cars. We're in Silicon Valley. Still need some more testing.
His name is South.
His name is South, yeah. So, again, the objective here was to produce pure hydrogen, as shown. And I did that by using the membrane reactor as a tool for natural gas steam reforming to produce that pure hydrogen that can be fed to a PEM fuel cell that can be used for onboard application within the transportation sector. Again, PEM fuel cell was used because the emissions are theoretically just water. On the back end, as a co-benefit of this process, we have a high partial pressure of CO2 that could potentially be captured. All right, so now to the exciting part. So the acknowledgements here. So I have a large committee here. So let's start first and foremost, Jen. Yeah, this has been a wonderful experience. Thank you for taking me on board as a student. I can think back 4 years ago when we were talking in your office there about potentially some projects that I can work on, and we sort of came up with this, at the time seemed like a crazy idea, but you know, thanks for having faith in me that this would really work out well. So thank you for that, and really thank you for having the, you know, when we were talking and I was like, hey, I have this roadblock here, you always knew where to network. Oh, go talk to this professor. Oh, go talk to that professor. Or, hey, maybe we need to hire somebody new in order to help you with some of your experiments. So, I mean, thank you very much for all that. Reggie Mitchell, Professor Reggie Mitchell, thank you very much for chairing today. I know it was sort of short notice, just 2 weeks ago or so, so thank you very much for that. And I can remember initially I went into your lab there to do some testing, so thank you for allowing me in your lab there. Professor Adam Brandt, I remember initially when I got into Stanford, I didn't really know what was going on. I mean, I don't know what this place was like. So I started making phone calls. No one returned my phone call, except Professor Adam Brandt here called me back. And he's like, hey, let's have a chat. So I was like, all right, cool. We set up this time. And you know, I'm like, all right, I'm all pumped to call him. I call him, there's no answer. And I was like, I've been dubbed. And then he calls me back like 5-10 minutes later, and he's like, oh, sorry, I'm on mountain time. There was a difference in time. So thank you very much for that initial phone call. And originally when I visited Stanford, we had a nice discussion about some of the research ongoing here. That was really comforting for me to know what was going on here. So thank you very much for that. Professor Chris Edwards. Yeah, wow. I mean, it's been I wasn't going to get there, but yeah, thank you very much for all your wonderful support. I know, you know, initially here when I came to Stanford, some of the best advice I got from another student was, if you have time, and if you don't have time, make time to have a class with Chris Edwards. And that was amazing. I mean, I was able to have the opportunity to have some classes with you. And I remember one time we were talking about an engine, and I was asking you some questions, and then the next time, you know, the next class, I was talking to you again, you're like, you know what, you asked some really good questions. And I felt very honored. Wow, this guy is a titan in his field telling me I have good questions. Wow, I went home with a big head that day. Thank you for that. Dr. Steve Pagliari, thank you very much. I mean, this is it's been a wonderful experience. Initially, when I tried this hydrogen work, I really didn't know what was going on. I was trying to tinker and stuff. And Jen, you know, got me in contact with you, and you were able to visit for a weekend. And I mean, we worked around the clock that weekend. Thank you very much. Yeah, that really planted that seed for the work to come. So thank you very much. And as a little teaser here, this is the original membrane that Steve bought. I told him I was going to bring it today. Here that we did some testing on. And a little story about this is, you know, the membrane itself is very delicate. That is, when they're brand new, you know, you shouldn't touch them or anything. You got to be very careful. Well, Steve stuck it in his backpack, which was fine. That's okay. I mean, he knows better than I do. And he got off the Stanford bus. Again, he came from Colorado, so he did all that traveling, came here. He stepped off the bus, and it got caught and bent the membrane. So the membrane came to the lab with like, it was almost like a U shape, and we're like, oh, we can just bend it back. So Steve, thanks for those wonderful memories. And of course, last but not least, Dr. Simona Lawari. I mean, wow, you've taken my research to a whole nother level. Really, thanks very much for that. Jen had the ability to hire you on, and initially when you showed up, I was just in the infancy stage. Don't cry, because you're gonna make me cry. Yeah, I mean, the words can express what you've done. Thank you. Grazie mille. The whole Clean Energy Conversions group, thank you guys so much. Shout out to Kyung Jin, thank you for helping me with those SEM images. Those post-analysis tests wouldn't have happened without you. Mang Yao, Ji-Yoon's not here, or Ja-Joon's not here. Ji-Yoon, thank you guys very much for, it's been like a family, and it's been great. Thank you very much. ERE department, I would like to thank the admin staff for all their wonderful support, specifically Yolanda for helping with all the back-end stuff of getting that all-important funding. Worcester Polytechnic and ITM for allowing me to visit there for 1 month's time. Of course, I got to thank my family. Here's, friends first, sorry. Friends first here. Yeah, that's been a wonderful time. Specific shout out to Phil and Jack. Thank you guys very much for all these wonderful memories. I want to point out this picture here. We were playing in the room over there with Phil's N64 or Nintendo, so thank you for that. Family, they've been rooting me on since the beginning. I'm sort of the first one to not only go to college, but graduate school. And they thought I was crazy, but they said, whatever you want to do, we support you. So yeah, thanks very much. I also want to give a shout out to my brother, Justin, that has Down syndrome. Here he has a Life Achievement Award. He just got last week, so. And of course, thank you, Michelle. It's been great. Thank you for all the support. Thank you guys for coming.
Yeah. I've worked on large-scale steam reforming with membrane reactors back in Canada, and I'm interested to see whether you can apply these kind of membranes in large scale, for example, gas-solid fluidized bed reactors for producing hydrogen.
I didn't specifically do that, but there are research papers on that, looking at, like, for example, coal gasification, for example. Yeah, but I didn't specifically look at that.
Do you know how sensitive is your membrane to erosion and plugging when you have a mobility of your, let's say, your catalyst inside a large-scale reactor?
Yeah. So there's actually testing that's a little bit different. This is the work here is shown as was a packed bed reactor. That is, the catalyst doesn't actually move within the reactor. But there is research for the fluidized bed. That is, the catalyst actually moves around within the reactor, and the membranes used there also perform very well for hydrogen selective purposes. Yep.
Okay. Just a quick second question. Can you compare, I'm interested now the LCA, it's an LCA project, the life cycle assessment of these kind of applications of introducing methane to a reactor and then producing H2 and then the vehicle, or comparing this scenario to just direct scenario of using methane?
Yeah. So I didn't have time today because the talk is supposed to be kind of short, but actually in my dissertation in chapter 12 specifically, I talk about the performance of the membrane reactor compared to the steam methane reforming process on a commercial scale. And is within good agreement in terms of thermal efficiency. So.
Any other questions?
So I don't know a lot about this, but you kind of sold me on it. So like, what's like preventing this from going commercial, basically?
Well, if I think graduation's in a month, maybe July and August, I can have you a unit. I didn't say what year though. What's preventing it? It's really the, the hybrid vehicles have come so far. That, again, this is outside of my realm here, but the hybrid vehicles have really come so far that they're quite efficient. But in terms of this specific application, there's some qualities of these membranes that sort of need to be overcome. That is, if we think of like the onboard application, for example, if you turn off your car and turn it back on, the thermal cycling of the membrane could potentially degrade that membrane. Yeah. So, but these membranes have shown under constant conditions that they're quite stable for years. And the reason I say years is because if you do an experimental test, I mean, the I think one of the longest tests was like 2.5 years. And if you like read the paper, the reason they turned it off is because they're like, okay, it's been 2.5 years and there's been 0 decrease in performance. So yeah, there's a couple issues with the membranes.
Any other questions? Yeah.
Have you seen the effect of the, let's say, the pore sizes of the porous media of your membrane? Were there some studies about how the pore sizes would affect the whole process?
Like the supporting material below?
Yes.
Or yeah. So the supporting material below, as shown, if you use the porous stainless steel, the pores are quite large. So when you actually plate that palladium on the surface there, it may not bridge the gap. So then it will not be fully selective towards hydrogen. So there has been studies on that. They're able to overcome that potentially by using, for example, the ceramic support, which has a smaller pore size that is nanometer scale when the layer is deposited on the surface.
Okay, so
Yeah.
smaller pores would make it more efficient.
Not that it'd be more efficient per se. It's sort of the two different supporting materials both have good and bad qualities to them. Yeah.
Can you talk a little bit about how you came to select the materials for the membrane to start with? Are palladium-based membranes common for natural gas reformation, or has no one done that before, or did you, just pick expensive sounding metals, or like?
Not just expensive sounding.
I originally thought I can use palladium, and then I thought, how can I increase the cost? So I alloyed it with gold. Just kidding. As shown, the selectivity of palladium, it's only selective towards hydrogen, so it won't allow any other gases to permeate through if the layer is dense. So that was sort of first and foremost. The reason here was to produce pure hydrogen. That's really the main benefit of that. Of course, as you alluded to, they could be potentially expensive, the membranes. So.
What's the reason palladium is selective to hydrogen compared to CO2, for example?
So as shown, the mechanism through the bulk, that is the hydrogen itself, diffuses on the surface and then permeates through the membrane as atomic hydrogen. So that hydrogen, the atomic, so H now, just H1, it actually moves through the crystal structure of the metal. No other gases are able to pass through. So if we think on like a really small scale of the palladium metal, that H is actually allowed to pass through the metal. So it does sound maybe a little strange at first, but yeah, that's how it works.
Well, what stops CO2 from doing that?
It can't fit through the palladium layer. It's too big.
Yeah, my question has to do with, so you talk, your structure you're talking mostly about the membranes, but there's also the catalyst as well. Can you talk about how the catalyst performed over the long periods of time scales that you experiments?
So again, for the experiments, you can do an entire PhD on just catalyst performance, for example. So what I did is I obtained a commercially steam within reforming catalyst that I know will operate for a very extended period of time. But to your specific question about the performance, I saw no decrease in performance of that nickel-based catalyst, which if I did, there would probably be an issue. That is that when you obtain these commercially, and this catalyst that I use is actually used within these large commercial scale processes that run for, months on end. But the idea sort of related to that catalyst is that I talk about in my dissertation is that you can maybe potentially enhance that performance. But again, that's sort of outside the scope of the work.
Any other questions?
I have one highly technical question that I have to ask in the open forum. On your very last slide, there was a little graphic in the bottom right. What was that?
You mean the barrel of oil?
Yes.
This guy? This is LP. This is my lucky pig. This is from Michelle. She gives it to me for good luck.
Go back to that.
This one?
I thought it was a little pig. That's great.
He's here. Yeah. Thank you.
Well done, Michelle.
And he's here if you want to say hi.